So, welcome everyone to our Friday seminar, which happens this week. It's happening in Durban. And the speaker is Graeme Pleasance, who is a postdoc at Stellenbosch University with Francesco. And he will give us a talk about his recent work related to the non-Markovianity in the collisional models.
Okay, cool. Thanks, Elia, for the introduction. And also, thanks for organizing this at relatively short notice. So my talk today will be on more or less open quantum systems theory. So more specifically looking at what are known as collision models. And also just to say that this was work that I recently did in collaboration with Professor Marco Merkley, who's at Memorial University in Canada, and also his master's student. Okay, I should say as well, if anybody has questions during the talk, either in person or online, please feel free just to raise your hand or interrupt and ask questions. Okay, so the kind of basic structure of my talk is I'll begin with a very brief introduction to open quantum systems for those of you who may not be familiar with open systems. Then talk about the basic formulation of collision models, what collision models are, how you can use them to model open quantum systems, and how you can characterize Markovianity in these types of models. Then look at kind of the adaptation of basic collision models to the non-Markovian regime. And then more specifically look at composite collision models, which can be used to kind of treat non-Markovian open systems in terms of Markovian ones. And then finally look at kind of an application to a particular example where we're interested in looking at how entanglement can affect the non-Markovianity of the dynamics. Okay, so the kind of the broad framework that I'm giving this talk is on open quantum systems. So a good place to start is defining what I mean by an open system. So essentially, it's any quantum system that is open and is able to exchange energy and information with its surrounding environment. And so the usual approach to treating these types of systems is to come up with some microscopic model for both the quantum system of interest and its environment. And so this is usually written down in the form of a Hamiltonian. So you have a system, environment, and an interaction contribution. And since in most applications we're only interested in the behavior of the quantum system and not in the environment, what we want to do is come up with a dynamical description of our quantum system, but one which only implicitly incorporates the effect of the environment. And so one way you can do this is by essentially using the Schrödinger equation. So the time evolution is prescribed through the Schrödinger or the von Neumann equation is given here. So it's essentially just a unitary time evolution for both the system and the environment. And as I said, because we don't maybe care so much about the environment, we want to incorporate the effects of the environment and the time evolution of our system, but without explicitly referencing its degrees of freedom. So what we can do is, in this second expression, is take the partial trace over the environment degrees of freedom. And if you make certain basic assumptions, which perhaps some of you are already familiar with, namely, if you assume that at some initial time that we denote t is equal to t0, if you assume that the system and environment are initially uncorrelated, this time evolution can be characterized in terms of what's known as a dynamical map. And so this dynamical map is formally a quantum, like a completely positive and trace-preserving map that takes as inputs states of our open system and maps it to other states of our system. And the way that you can represent this is in the following way. And this kind of structure guarantees the complete positivity of the evolution. Okay, so that's how this is kind of like a very brief intro into the kind of the canonical approach to dealing with open quantum systems, where we have a macroscopic continuous environment and where all of the degrees of freedom of the environment simultaneously interact with the system. But there's a kind of alternative paradigm to treating open systems, and that's in terms of what's known as collision models. And so collision models are different from the previous setup that I just mentioned insofar that rather than having a continuous macroscopic environment where all of its components simultaneously interact with the system, in the collision model, your environment is decomposed into into many discrete identical ancillas. And the way that you model interactions between the system and environment in this framework is each of these ancillas interacts with your system of interest here, S, in a stepwise fashion. So here, A1, A2, A3 labels all these ancillas of the environment up to some finite number. And then we assume that collisions or stepwise interactions occurs between each of these ancillas with the system. And so, hence the name collision models, you can kind of intuitively think of a particle coming in, interacting with the system, and then being scattered off, and then the same process repeated over and over again. And so these collisions or interactions between each ancilla and the system are modeled usually as unitary interaction. So what we can do is specify some kind of unitary map here, this calligraphic U, which basically tells us how system and a given ancilla J evolve under some kind of interaction. And so every time the system interacts with an ancilla and you move along the chain, a new ancilla is added at the end. And so kind of the general structure of the states on this Hilbert space is given in the following. So you have essentially the system with the tensor product of many ancillas all the way up to some nth ancilla. Okay, and so collision models aren't exactly new. They've been around in the literature for a while, but one of the reasons why they're of interest is because partly due to the kind of the conceptual simplicity of the framework, but also due to the versatility. So you can kind of tweak many aspects of this type of model. So how the ancillas interact, the initial conditions of the ancillas, et cetera, to kind of describe many types of physical systems. And so some, well-known examples are in quantum optics, also in non-equilibrium quantum thermodynamics. I've also seen some papers which look at quantum models of quantum gravity using collision models. Okay, so what we'll do is kind of start by looking at the kind of the very basic, most simple type of collision model. And then throughout the talk, I'll look at kind of generalizing this to slightly more complicated situations. And so in the most basic collision model, what we have is, as I said, an environment that's made up of many ancillas, and we assume that all the components in our system are initially uncorrelated. So in other words, we can write down if we want to write down the initial state of our system, we just write it down as essentially well, the state essentially factorizes into each of the components of system ancilla 1 or the ancilla n. And we assume that the system only collides with each ancilla on one occasion. And so once the ancilla is interacting with the system, it effectively doesn't interact with it anymore. And so what that implies is that we can write the here I'll say time evolution. Yep, sorry.
Because I understand it's in terms of calculating the dynamically in quantum conversation.
Yeah, so ancilla in this context just means any system with a finite dimensional state space, I think. So it's it could be something like a qubit or a harmonic oscillator, but essentially it's something which is discrete and something, yeah. Okay, so I should also say that maybe also that terminology ancilla is kind of partly adopted from the fact that it's used in quantum computing as well, maybe, I don't know, but yeah. But anyway, so okay, if we assume that the system collides with each ancilla once, that implies that what we can do is write down the density matrix of our system plus environment up to some nth collision. So here, even though this index n doesn't necessarily represent time, I'll say dynamics to mean essentially to imply a system that undergoes many interactions with ancillas. Okay, so the dynamics of the full system and environment can be written in this way. So essentially, it's just you take the unitary map corresponding to the interaction between the system and ancilla 1. You then compose it with the map for the system in the second ancilla, etc., all the way up to the nth ancilla. And so essentially, you kind of get this nested kind of nested expression in terms of these unitary operators. So each of these unitaries describes the evolution of the interaction between your system and first ancilla, system and second ancilla, etc., all the way up to the last ancilla. And kind of importantly, we don't assume any collisions between ancillas themselves. So as I kind of mentioned, this is how we kind of describe time evolution in terms of this composition of many unitary maps. And what we also do is assume that each of these ancillas are identical in the sense that they're all prepared in the same state, which here I denote by sigma. And so, as I kind of said at the beginning, we're generally in the framework of open quantum systems, we usually only care about the system of interest, S, rather than the environment. So what we can do is, to obtain the reduced density matrix of our system, we just trace out all the ancillas from the first expression. And so what you can see is that because so if you look at this kind of nested structure on the first line, this U here only acts on system and ancilla 1, the next U only acts on system ancilla 2, etc., all the way up to the last one that acts on the system and ancilla N. And so what this implies is that you can kind of draw each of the partial traces through up until the point it hits an operator which involves the ancilla, which is denoted by the A1 or the AN-1 index, etc. And so from this, we can define a dynamical map or some kind of quantum map analogous to the one I introduced in the first slide, which essentially is defined in the following way. So what this does is the structure of this expression is essentially the same as the one I gave on the first slide, and so that guarantees kind of complete positivity. And so essentially this represents a valid physical evolution of our system at each iteration of the dynamics. Okay, and so if we define the map in this way, if we want to look at how our reduced system evolves after n collisions, what we do is we just essentially take the initial state of our reduced system, apply this map phi, and then just apply the map phi again, iteratively all the way up to the however many ancillas are involved, so n times essentially. And effectively, this is kind of expressed here. So we're just taking the nth power of this map. And so kind of conceptually, the way you can kind of visualize this is in kind of the right-hand side here. And so for the first collision, so when n is equal to 1, what happens is our system interacts with ancilla A1 via this unitary U. And then if I maybe just quickly go back to this previous expression here. So what we see is that we have our system, this initial state of our system and initial state of our ancilla initially uncorrelated. They unitarily evolve according to this U, and then we take the trace over what ancilla is the system has just interacted with. And so in the right side, this is kind of on the right-hand side of this slide, this is what's being graphically represented. So we have system ancilla A1 interaction, and then we apply this partial trace operation. And effectively what this partial trace operation does is effectively just remove that ancilla from the description. Or in other words, we're removing any information that ancilla has on the system after its interaction. And so kind of the way you can, or I should say that, so this kind of basic description where we can construct a map which is effectively the iteration of n maps represents a purely Markovian dynamics. And so what do I mean by that? So essentially a Markovian dynamics is one where there's no memory incorporated into the time evolution of our system, or it describes the memoryless process. And so one way you can kind of understand that is by kind of visualizing it down here at the bottom. So at the nth collision, we have whatever the state of our reduced system is, rho S. We then, according to this operation that's described up here, what we do is we then just apply another, so to go from n to n plus 1, we just apply another iteration of this map phi. And then that's essentially what these two sequences here describe. So this next iteration, we do the interaction between the system and ancilla an plus 1. And so generally what happens is that after the system and the ancilla interact, they become correlated in some way. They share some kind of correlations. But then what happens is that when we apply this partial trace operation, so the operation that's encoded in each of these maps, is that we effectively destroy these correlations and just or erase these correlations from the description, and then another ancilla, which was in this state sigma, immediately replaces the one that's just interacted. And so the way you can kind of maybe conceptualize how this describes a Markovian or memoryist dynamics is in the sense that over successive collisions, there's no memory that's retained between, or no memory that's retained across successive collisions. So after the system interacts with the given ancilla, any information this ancilla holds is immediately destroyed and thrown away, and then a fresh ancilla in the previous state is immediately replaces it. Okay, so the kind of important thing to take away here really is this idea that basic collision models describe a purely Markovian dynamics because we can write the map describing the evolution of our reduced system as the iteration of n completely positive maps. Okay, and so a way that you can kind of characterize this more formally is in terms of a concept that's known as divisibility. And so what we can do is kind of consider a one parameter family of completely positive trace preserving maps. And more generally, so if we have some map here that now depends on this parameter n, which is just essentially any natural number, so it's 1, 2, 3, etc., where this n counts the number of collisions, we say that this map is divisible if it basically satisfies this property for all n and m. So in other words, we can basically write this, we can define an intermediate map, which depends on two parameters. And if for all n and m, this intermediate map is completely positive and trace preserving, then our map phi of n is completely positive and trace preserving also. Oh, sorry, the map phi of n is divisible. Okay, so applying this concept to our previous example, where we can, so in the basic example that I gave on the previous slide, we can write this map phi of n. So essentially, this is just a map that describes the reduced state of our system after n collisions. And I mentioned that this is, we can just write this as essentially the nth iteration of some basic map phi. Okay, and so the way we can see, according to this divisibility criteria, that it's the way that we can see that this map is this map phi n in the basic example is divisible is through the following. So okay, if we just look at this divisible map, it will just be given as phi of n to the power of n minus m, and that just follows directly from the fact that this relationship holds. So looking at here, if we want to evaluate phi of n, what we do is just take phi to the power of m and then multiply this by phi to the power of n minus m, and then obviously this just gives us phi to the power of n, which is just this map here. And so generally, one way of defining non-Markovianity is in terms of this concept of divisibility. So if a map is divisible, it's said to describe a Markovian process. Okay, so for that previous or the basic collision model that I introduced on the previous slide, it describes a Markovian dynamics because the map phi n here that you use to describe the dynamics is always divisible. Okay, and so another way that you can also kind of characterize Markovianity is in terms of what's known as the trace distance. And so trace distance is just a kind of measure that it represents essentially a metric on some state space. So it basically computes the distance between any two states. But a kind of one way of characterizing Markovianity in terms of this trace distance is through kind of a non-monotonic behavior of this quantity. So there's a kind of general I guess called general theorem that tells you that for any, if you take this expression and you apply some completely positive map on rho n and sigma n, this can only decrease the trace distance between these two states. Okay. But what you can also show is that if you have maps which are non-completely positive, then you can potentially increase the momentarily increase the trace distance. So that occurs in cases where the map up here isn't necessarily divisible. Okay. And so this non-monoticity of this trace distance implies non-divisibility, and so that's what we that's the way that we can kind of formally characterize non-Markovian processes. But just to point out that this generally isn't a kind of bidirectional relationship. So if you have non-monoticity of the trace distance, this always implies the map to be non-divisible, but the reverse relationship isn't generally true. Okay, so that was kind of like an outline of basic collision models and the fact that they can only describe purely Markovian dynamics. So one's dynamics that has no memory involved. And so now what we want to do is kind of look at a generalization of these previous models to ones that are capable of describing non-Markovian processes. And so there's kind of many different strategies in the literature for doing this. I won't kind of go over all of them, but I'll mention two that are kind of particularly relevant to what I'll show you in the latter half of the talk. And so, but whilst there are the kind of many of these ways of formulating non-Markovian collision models, they're all kind of based conceptually on this idea that in order to make the reduced dynamics non-Markovian, you have to introduce some kind of feedback mechanism that allows information that is passed into the environment through system ancillary interactions to come back to the system at some kind of later point in its evolution. Usually this is kind of mediated through system environment correlations, okay? And so one kind of feedback mechanism or scheme that's kind of very commonly used is basically modifying the previous model to also include collisions between ancillas. So previously what we had is a system that just interacted with each ancilla. So S interacted with A1, A1 left, S interacted with A2, A2 left, etc. But now we have a kind of an additional step that's included where S interacts with A1, but then A1 interacts with A2, and then A1 leaves, and then S interacts with A2, etc., etc. And so kind of conceptually, or I should say, okay, formally, you can kind of construct the density matrix of your system plus environment in this way. So now rather than just being the composition of n unitary maps, you also have these additional maps, which here I call W, which describe collisions between ancillas. So here, just for simplicity, we're just looking at collisions between kind of pairwise collisions between nearest ancillas. Okay, you can have potentially more complicated situations where you have multiple collisions between many ancillas, but here let's just focus on the simplest case. And so this is essentially these two indices denote the two ancillas that collide with each other. Okay. But in this case, you still generally assume that the environment is initially uncorrelated or the full state initially factorizes. Yes.
I know that it's only the unitary that involve the system is unified.
Yes.
In terms of U1, U2, U3,
so you mean the index? What does it refer to? Like the U1. So the index of U1 refers to the fact that it involves interaction between the system and ancilla A1. So it describes essentially the interaction between these two things. So U2 describes the interaction between S and A2.
Do you mean your environment is, I mean, you are able to control your incident in your environment?
Yeah.
So that you only have interaction. I mean, the interaction is successive. Like,
yeah, so that's a kind of like a general, that's essentially what defines a collision model, is the fact that the interactions are successive. So they happen one after the other.
one after.
Yeah.
would be able to do that? You have some controls system.
I mean, previously I gave examples of kind of applications. So things like, for example, in quantum optics, there's physical examples in those types of systems. I know one example was something like a micromaser, where you can, I think collision models have been used to treat these types of systems. So basically where, one type of system could be where maybe in quantum optics is where you have a kind of cavity, you have a single mode cavity. This is like your system, and then you have a kind of stream of atoms or particles that kind of passes through the cavity. And then as this is your cavity, this is like a stream of particles, and each of these particles comes in, interacts with the cavity field over some time, and then leaves, and then the next one comes. So there are physical systems where you can kind of replicate this type of successive interaction like structure. But I mean, more generally, I guess why people are also interested in them is because they're able to replicate kind of generic features of open quantum system dynamics. So things like decoherence and dissipation and things. So even though your system may not directly, you might not be able to directly map your physical system onto this structure, you can kind of maybe in a sense model it in this way because it's kind of easier to do, maybe. Yeah. Okay, so yeah, so this is kind of one generalization of the basic model to non-Markovian collision models. Another such generalization is where we relax the assumption that all the ancillas are initially uncorrelated. So what that implies is that you still have, so as in the basic model, you still have only a single interaction between the system and each ancilla, but you start in a state where all these ancillas are correlated with each other. And so that's just kind of expressed here. So the state here, sigma n, is you can't generally write it as a product of n ancillas. Okay, so these are kind of two ways that you can kind of generalize the basic model. And so what I'll do now is kind of focus on the first one. So focus on the first type of non-Markovian collision model where you have ancillar-ancillar interactions. And so more specifically, what I'll do is I'll kind of highlight a kind of result of a paper that was published in PRA in 2018 by Campbell and others, which demonstrated for these types of models, you can essentially map your non-Markovian dynamics onto an enlarged system which undergoes some kind of Markovian dynamics. Okay, so as I had before, the state of our system in that environment is written here. And so this is just a full dynamical description of our model. Again, we're only interested in the reduced system. So how do we get the reduced system state? We take the partial trace over all the ancillas. And so that's essentially what we do here. And what you can kind of do is do a kind of clever rewriting of this expression, which at first might not seem particularly interesting, but it allows you to kind of come up with an interesting equivalent representation of the dynamics. So what you can do, I'm skipping over kind of technical details here, but what you can do is rewrite the top line in terms of this expression here, where what you do is change each of these indices on the U's to just 1, and then attach to every W a kind of swap map. So that's kind of indicated by this prime here. So this W prime is just kind of the map that describes collisions between nearest neighbor ancillas and some kind of swap map. So a swap map is essentially, well, it has this structure here, but what it essentially does is it just takes any two states. So if you have a bipartite system, so in this case, two ancillas, what it does is it takes as input this product, and then it just flips the states on the two state spaces. Okay. So again, this might seem a little bit strange why you want to do this, but why it's interesting is because this expression exhibits the kind of the same structure that I illustrated for the basic collision model. So if you recall, in the Markovian collision model, you could write the time evolution of or the dynamics of your reduced system as the iteration of some map n times. And it turns out that if you do the same thing here, so if you rewrite the expression this way, you can do the same thing. So you can define a map here, which is phi, which I call, I've included the superscript here too, which will maybe become a bit more obvious just now. But we take this map phi 2 and apply it n times to the initial state of our system plus a single ancilla, which here I just call A1. And then we just iterate it n times and then trace out the ancilla A1 to get the reduced state of our system. And so what this phi 2 is essentially it's a map in the same way that, you know, the phi that I introduced before, but it doesn't just map between states of our system, it maps between states of our system plus one additional ancilla. So it basically has this kind of formally, it has this structure, which you can verify to be, again, CPTP from, you know, Steinstein's theorem. Okay, so why is this interesting? Is because essentially it describes the kind of a kind of graphic representation of what this expression up here describes is given here. So what we have now is, rather than having a system that interacts with a kind of chain of ancillas and then the ancillas interact between themselves, what we've done is effectively mapped it to a different representation where our system interacts with an ancilla A1, but this ancilla A1 is kind of permanently kept in the dynamics and it's not traced out in the same way that we did before. And then this ancilla A1 interacts in turn with an ancilla A2, which is then traced out. And then this is replaced by the next ancilla. These two things, so the system and A1 interact again. And then these two ancillas interact via this map and then, you know, before. So basically, the difference that we had before is that this ancilla A1 is now kept permanently in the dynamics, it's not traced out and thrown away. And kind of you can conceptually view this as what we've basically done is kind of partitioned our initial environment into an explicit memory part and a non-memory part. And so why does this ancilla A1 represent the memory is because it basically encodes the system environment correlations that are what I say relevant to the dynamics. So basically it's system environment correlations that we can't erase through a trace operation without generally non-trivially affecting the dynamics. Whereas this other component, this non-memory component, it represents a part of the environment where we can basically repeatedly throw away correlations at every stage without affecting the system dynamics. And so what we can do is kind of define an enlarged system, which is our original system S plus this additional ancilla A1. And collectively, this new kind of super system, if you want to call it that, undergoes a Markovian dynamics according to this kind of iterative procedure that I gave in the, you know, previously for the basic collision model. So, so this kind of picture is quite conceptually important. So, I mean, for those of you who have listened to my, you know, talks before, maybe it's just Ilya, one of the kind of methods that I'm interested in is this so-called pseudo method and reaction coordinate mapping, which these aren't methods that apply to collision models, but they are based kind of on conceptually similar idea of transforming a non-Markovian system to a Markovian one by kind of embedding degrees of freedom of your environment into the system. And so this is kind of essentially conceptually the same as that type of approach. Okay, so that's kind of like a very brief history of collision models. What I'll now do is, I'm not sure how long I have left, but yeah, I'll just keep going. But I'll talk more specifically about the work that I did together with collaborators. So, so what we did is we looked at a kind of specifically a non-Markovian collision model, but one which kind of is a variation of previous types of non-Markovian collision models in the sense that we assume an environment that is initially correlated. So all of the ancillas are correlated, but we kind of do it in an operational way rather than just specifying some state which is correlated. What we do is we introduce these kind of super operator maps, which kind of sequentially correlate groups of ancillas all the way up to some kind of finite number n. And so kind of visually, I mean, this is formally the way that you represent the initial state of your system environment. So here the system is initially uncorrelated with the environment, but this kind of thing here is going to be correlated generally. And the way this might look like a little bit of an artificial setup, but kind of one way you can think about it physically is the following. So you have this kind of system here, you have a chain of ancillas. You can kind of visualize these ancillas as kind of being generated from some kind of gun or something, or something, whatever. Each of these ancillas is initialized in the same state. But before these ancillas interact with the system, they kind of undergo, there's some kind of tube which applies some kind of operation to some group of ancillas, and the size of this group is denoted by this parameter L. So in this kind of schematic, this is the example for L is equal to 3. So you have a map here that before the ancillas interact with the system, they get correlated through some kind of operation that applies to 3 ancillas. But also the kind of important thing to point out is that this operation is done sequentially on consecutive groups of ancillas. So you start with the first group of, say, 3 ancillas, and then you go to the next group, but these groups are generally overlapping with each other. Okay. And so, okay, we just looked at a case where this is a kind of this operation is described by some arbitrary unitary map, but you could, in principle, look at some, you could just have a non-unitary, a more general type of CP operation, so like a non-unitary map or something. And so what this W does is it basically takes groups of ancillas that start at the label J, so ancilla AJ, all the way up to ancilla with this index, so L plus J minus 1. And then it does that sequentially for lots of groups of ancillas before they interact with the system. And so you have this initially correlated state, and then in the same way as we had previously, okay, there's a little bit of there's a typo here. There shouldn't be an uncorrelated state, so let's just ignore this bit. But the dynamics is the same as what we had previously in the basic model. So where we just apply a sequence of unitary operations between the system and ancilla A1 and system ancilla A2, et cetera, et cetera. Okay, so in all the examples that I gave previously, how do we get the reduced system dynamics? We trace over all the ancillas. So we just do the same procedure here. And what I'll do in the following is just focus on the case of L is equal to 2. So that corresponds to the case where we only have pairwise correlated ancillas before they interact with the system. And so in this type of setup, I'm skipping over some kind of technical detail here, but what you can do is kind of something similar to what I demonstrated in the example where you had non-Markovian models with collisions between ancillas. You can basically, in other words, what you can do is you can write an expression for the reduced density matrix of your system that has an iterative structure in terms of some map that I call psi here. So this is just to differentiate it from the previous map that I defined. But it follows the kind of the same prescription that we had before, where what we can do is, in the case of L is equal to 2, is to incorporate an extra ancilla into our system. And by doing so, we can make a Markovian dynamics, which has this kind of explicit structure. And so similar to before, this kind of map psi 2 is formally defined in this way. But how this approach differs from the previous one, so where we had ancilla collisions, is the following. And so I won't go back to the expression, but previously in the previous model I had, the map had a very similar structure, but instead of U being here and W prime being here, they were basically switched. And also this U only acted on ancilla A1, not on ancilla A2. So maybe I can just very quickly go back to this slide. So if you can recall, in this previous example, our kind of the definition of this map phi 2 gives rise to this kind of representation of the reduced system dynamics in terms of this enlarged Markovian system. So in this kind of model with initial correlations, what we can do is something similar, but the composite model that you, or the kind of the equivalent representation of the dynamics that you get has this kind of distinct difference in that the kind of the configuration of the ancillas is inherently different. So before, what happened is that the system S interacted with the memory ancilla A1, which in turn interacted with the memory memoryless environment, which comprise all the ancillas A2 up to ancilla N. But in this example, what happens is that the system doesn't directly interact with the ancilla A1. It only interacts with the memory ancilla, only interacts with A1 through A2. So you can kind of see that this describes a kind of qualitatively different dynamics.
Order first system and
So it's the opposite order. So previously it was S and A1 first,
yes.
then A1, A2. But now the order has changed. So it's A1, A2, then S, A2, and then A2 is traced, and then P repeat. Yeah, so, and this kind of, this kind of has clear implications for the non-Markovianity of the dynamics. Yeah, so I should just, before I finish this section, I should say that
Essentially, will have less memory because if you interact A1, A2, so you kind of like you kind of impart part of the memory from A1, which is your memory cell, to the A2, and that memory is affecting S, but after you throw away.
Yeah, that's actually what I thought. That was my original interpretation, but in the application that we looked at, it actually is the opposite. This one is actually more non-Markovian than the one with the reverse, but that's the same interpretation that I had initially, because if you think, is that because these directly interact, it's going to, in a sense, generally going to share more information with this ancilla than this one, or the correlations will be stronger. So when you delete these correlations, you're kind of deleting more memory compared to this one. Or in other words, this A1 is going to generally be more weakly correlated with this, but so maybe kind of one takeaway is that what the kind of main kind of conclusion of this kind of mapping is for this type of model is that you can kind of, there's a direct correspondence between collision models where system environment correlations are kind of dynamically generated. So what you have is system ancilla A1, ancilla A2, system interacts with ancilla A1, A1 interacts with A2, this then goes on, S, A2, etc. And kind of correlations are sequentially generated between all these components as they go on. And these correlations encode the memory and the dynamics. And so these are kind of dynamically generated correlations because they occur through collisions. In this type of example, the collisions are kind of, or the correlations are only included in the initial state. So they're kind of statically generated. But what this result shows is that you can kind of treat these two things in the same way, whereby, you can come up with an equivalent description of dynamics where these correlations are kind of included dynamically, in the setup. But obviously there's kind of clear differences in how you do that based on the composition of the system and ancillas. Okay, so that's maybe the more formal part of the talk out of the way. So in the last maybe 5-10 minutes, I'll just look at an application. So, we essentially just looked at pretty much almost the simplest model that you can get, which is just an all-qubit collision models where the system is a two-level system, our open system S is a two-level system, every ancilla in the environment is a two-level system. And we looked at a particular example where we have these types of operations. So we, the interaction between each system and each ancilla J is just described by this operation, which depends on this parameter tau. And then we focus on the case of L is equal to 2. So that's when you only have nearest neighbor correlated ancillas in the environment. And that's generated through this operation, which is a kind of Pauli Z. So this is a kind of Pauli X interaction. This is a kind of Pauli Z interaction. And each of these depends on some parameter here that we call tau and epsilon. So essentially what these parameters represent is that so I call this the interaction phase because it essentially determines how the system and each ancilla interact. And then this epsilon is a kind of entanglement phase. So what I'll show is that it basically determines, based on the value of this epsilon, it determines how entangled these ancillas are in the initial environment before they interact with the system. And I should also just point out is that, so at the beginning I said that we were interested in this application, specifically looking at the role of entanglement in determining the non-Markovianity of the dynamics, or kind of simply, if we tune up the entanglement, does it make the dynamics more non-Markovian or not, or can it make the dynamics more non-Markovian? And so Okay, so we have this kind of basic setup. We also assume each of our ancillas are initialized in the same state, and we're for simplicity, considering that we have this Pauli Z operation, what we do is we assume that each of the initial states of ancillas is just a kind of 1-1-1-1 state. So it's basically in the block sphere, just the state that points in the positive x direction. So specifically, we choose this initial state because it's a state which can get entangled under this operation. So obviously, there's certain choices of states that, for example, if you chose the 1-0-0-1 state, this wouldn't get entangled by this operation because it's effectively an eigenstate of Pauli Z. Okay, so I should also say, okay, with this particular setup, I'm skipping out quite a few technical details, but you can show that the reduced dynamics of your system effectively only, you have a kind of decoherent interaction. So only the coherences of your system get decay over time. The populations remain invariant. So it's kind of like a dephasing or a decoherence interaction. So, and you can express it in this way where this function here, D, is, we call the decoherence function. Okay, so I said we were kind of interested in looking at the role of the entanglement, like how, if we change the entanglement, does it make the dynamics more non-Markovian or not? So the way that we, since this is a qubit model, the way that we quantify entanglement is through the 2-qubit concurrence. In this case, it has a relatively simple analytic expression. It's just essentially sign. So if you look at how it depends on this parameter epsilon, in the range of 0 to pi over 2, effectively, if we set, it just increases up to its maximum value. The concurrence increases up to its maximum value of 1 when epsilon is pi over 4, and then just decreases back down again. So this kind of, with this type of interaction, we're able to tune between the completely non-entangled and the maximally entangled regime. Okay, so this is kind of the result. So these are still somewhat preliminary, but the way that we quantify non-Markovianity is in terms of this kind of trace distance measure that I mentioned earlier. And what you can do is kind of well known in the literature is you can introduce this kind of measure, which is known as the BLP measure of non-Markovianity, which basically just basically sums over. So the way that you quantify this measure is you just sum over all intervals, so all successive intervals in the dynamics, and you include any parts of the dynamics where the trace distance increases at some particular step. So if you can recall, I said that this trace distance measure witnesses non-Markovianity in the sense that if it displays non-monotonic behavior, the dynamics is non-Markovian. So conversely, if you have purely monotonic decay of this trace distance, then it's Markovian. Okay, I should have probably used a different notation here because this is just to emphasize, this here is the trace distance. This quantity here is the decoherence function, but I should have probably used a different notation. But what you can show is that in this model, because it only undergoes a dephasing dynamics, is that a sufficient condition for non-Markovianity is the following. So basically, where a step where the modulus of this decoherence function increases from n to n+1. Okay, and on the right-hand side, what we have here is kind of a plot of this measure in the epsilon tau plane. And so the dark regions indicate points where the measure is basically 0, so where the dynamics is Markovian. And the bright regions are where there's maximum. So here you can see that obviously like the bright regions here is where the non-Markovianity is maximum for each of these values of epsilon tau, whereas this region here is basically purely Markovian. And kind of some interesting features of this plot, I think, are, well, firstly, the first thing to point out is that there seems to be this inherent asymmetry between if you fix a value of epsilon and then vary tau, and if you fix a value of tau and vary epsilon. So what I mean by that is the following. So what we can do is kind of focus on a region of this epsilon tau plane where there does seem to be kind of non-trivial non-Markovian behavior. So in this case, where let's just set epsilon to 0.2 pi, which is kind of what we're doing is just kind of taking a slice of this plot here along this kind of axis. And then what these plots show here in this area is the decoherence function plotted for essentially 50 different points along like this axis up here. And so each of these kind of lines is colored according to how non-Markovian the dynamics is according to this BRP measure. So each of these kind of grayed out lines are just purely Markovian. It's where the measure is 0. These kind of, as I said, the colored lines indicate there isn't a color map here, but basically the more yellow it is, the more non-Markovian it is. And so you can see here, so here we fixed epsilon, and then we're varying this interaction phase tau. And you can see that it kind of has this inherent asymmetry. So in other words, if you increase tau from 0 to pi over 4, the non-Markovianity kind of goes up and then goes to 0, and then it displays the same behavior when you go in the other up all the way up to pi over 2. But what's kind of interesting is that the other kind of side is not the same. So what I mean by that is, if you fix the interaction phase and then you change the entanglement parameter, the non-Markovianity isn't symmetric about pi over 4. And perhaps why this is interesting is because if you recall on the previous slide, I showed the behavior of the concurrence in the interval of 0 to pi over 2. And basically it just went up to its maximum at pi over 4 and then went down again to 0 at pi over 2. But it's symmetric about that interval, right? But here you can see that kind of the non-Markovianity is asymmetric. So this kind of red dashed line on the plot here and also on this 2D plot indicates the value of epsilon where the concurrence is maximum. And similarly, like either side of this red line, the entanglement is symmetric. But we see here that the non-Markovianity is much higher here than it is, for example, here, despite there being the same concurrence. So this would indicate that maybe there's other correlations that are having some effect on the non-Markovianity. But also the kind of the important, perhaps the most important thing to point out is, interesting in this model, you can see that when the concurrence is large, so when you approach pi over 4, the non-Markovianity generally peaks, at least within certain regions of this plane. But when you get to the maximum entanglement of pi over 4, the non-Markovianity vanishes. So basically it becomes completely Markovian. And you can actually prove this. So maybe I'm not, not just looking at this plot, but you can basically demonstrate that in this example. When, yeah. Okay, yeah, at least when the entanglement is maximum, you get no memory effects in the dynamics. Okay, so that's pretty much the end of the talk. So okay, this is just a very brief summary. Essentially, the main things to kind of take away is that basic collision models where you have initially uncorrelated environments and you only have single collisions between the system and each ancilla, describe a purely Markovian dynamics. And you can show, one way you can formally show that is the fact that the dynamical map that describes the system evolution up to some finite number of collisions is by construction divisible. The way that you generalize this then to non-Markovian collision models is by kind of breaking this divisibility by introducing feedback mechanisms that kind of introduce system environment correlations that, as I said, break this kind of underlying divisibility of the system dynamical map. And then what I did was kind of establish the idea of mapping a non-Markovian collision model, the open dynamics of a non-Markovian collision model, onto a Markovian one by incorporating extra ancillas of the environment into the system. And then I looked at a particular example of where an application of our result to an all-qubit collision model to look at the role of entanglement on the non-Markovianity, and you can see that whilst entanglement can enhance the non-Markovianity, it can also kind of completely suppress it, especially at the point where there's a maximum entanglement ancillas. Okay, and so just to kind of say that a lot of this work was done in collaboration with Professor Marco Merkley, who's actually a mathematician. So he's at Memorial University in Canada, and this is also partly done with his master's student, Angel, and also with Prof. Training at Stellenbosch. Okay, so yeah, thank you.
Thank you very much, Graeme, for the very interesting talk. And are there any questions?
To properly understand this successive action.
I know in normal, I mean, in real condition, you won't be able to, I mean, it would be very hard to make this successive interaction. The ancilla will not always be based on that. So they were able to get the success.
Yeah.
I mean, in that case, usually this will so far, like case we are not able to
Yeah. Yeah, so I guess 2 points about that. So I mean, there are certain physical systems that do replicate that property, but again, maybe those are very specific physical systems. So I gave the example of like kind of the cavity system where you have a kind of stream of atoms that go through the cavity. I mean, that's just one particular physical example, but I mean, I also mentioned that these types of models can't necessarily just be applied to systems that exactly physically replicate this kind of successive interaction structure. You can use these types of models as effectively simulation tools for other types of systems. So if you think in terms of things like, for example, quantum computers, they basically simulate physical systems using effectively sequences of unitary gates, where you have a register of qubits and then you apply operations between these qubits. You can kind of think of that's what you're kind of doing here with these types of models, is that effectively you have ancillas, in the all-qubit model that I looked at, you have a system which is a system which is two-level system, or qubit, all your environments are qubits, and you're basically just applying gates between all these kind of components, which is in a way kind of like a quantum computer, really. So I take your point that like these types of systems might not have an exact physical representation in certain situations, but they can also be used as kind of simulation tools for kind of exploring other kind of effects. Yeah.
First comment is why at maximum entanglement it's not surprising that there is no Markovianity. It's very simple. Because you have a bipartite system, if it's maximally entangled, you have an entanglement in monogamy. Yes, so you cannot entangle anything else to that.
Right. Yeah.
And that's automatically implies, because memory effects is some sort of correlation. So, but you cannot, if they're maximally entangled, they cannot accept any more correlation into that enlarged system because these two guys are already maximally entangled. And that's perfectly fine, correlated to the fact that if you decrease a little bit of entanglement, suddenly you can get maximum non-Markovianity.
Yeah.
Because suddenly there is a space for the tripartite entanglement or something like
Okay.
that.
Yeah.
When you're bipartite maximal entanglement, there is just no space, and that's
Okay.
Dictate the properties of your channel automatically.
Okay.
And another comment is, on some stage, there was papers of large geometry with a very similar line of thoughts that you have sequences of qubits, and you were tracing out them kind of like slower. You're not tracing out immediately qubit, but you kind of like qubit of interest, 2 or 3 qubits interacting, and you kind of like you add one more interaction, you interact over the chain, and you cut the last qubit.
Okay.
And kind of as a function of the number of qubits, you get a different non-Markovianity regimes in the dynamics.
Okay.
That's my Yoshi's papers at some stage. So that might be.
Yeah. I don't think I've seen those papers.
I understand if you do the larger L, you will have like more qubits in the memory system. Yes.
Yeah. So we just looked at that's essentially a limitation, especially if you want to do simulations, is that the larger the L, the more qubits you have to include in the map. And at least the limit that I pushed it to I haven't included those results, but I think I tried up to L is equal to 4, but even then it was like very difficult to do simulations. So basically, I didn't say this, but the way that we basically kind of explicitly solve this model is by just taking this map and kind of coming up with a Liouville representation of the map. So a matrix representation like a double Hilbert space. So in the case of L is equal to 2, you're dealing with a 4-dimensional system, which is already going to be like a 16 by 16 matrix. So if you go to L is equal to 3, this size just grows exponentially. So that's kind of limitation.
Like you're trying to do analytically in Mathematica or numerically?
Well, we came up with an analytic expression for this matrix in terms of other matrices, and then you can express this map here as kind of powers of matrices. So we looked at, can you actually compute these powers of these matrices, you know, using some trick, but we couldn't find anything. So we just did that. We did that part numerically, but we have, at least in the L is equal to 2 case for the example that we had like an explicit matrix representation of the map in a kind of doubled Hilbert space, yeah. But that only really works for the L is equal to 2, because if you go to L is equal to 3, it just becomes too big.
What are you using for numerics? Python?
Python. So yes. So yeah. Yeah. I'm not sure where the kind of computational bottleneck is, because in principle, I mean, we did this kind of analytically with a little bit of help from Python, but for higher L, you can, I mean, I did it, you know, using, there are packages like Qtip where you have these types of super operator representations of things. So you can just explicitly encode this in that, which would be a sparse matrix. But I do have code to do that, but it was kind of very slow for L is equal to 4, L is, you know, so I'm not exactly sure what the bottleneck is, but it's already very slow for like L is equal to 4, yeah.
But once you get the Qtips, because what you get in Qtip, they sometimes, for some comments, they have to convert stuff back to dense matrices, and that's where it's all that stuff. Sparse matrices, you should be able to
yeah, I can maybe check to see where that issue is, yeah, because essentially, yeah, all you're doing is matrix multiplication. So if you're able to come up with I don't think there's any issue with storing the matrix in memory, like, all you're doing is matrix multiplication. So I'm not sure.
And your matrices are sparse, because looking at your interaction, you're in a very good case with sparse.
Yeah, and so in the analytic case that we looked at, like, yeah, it is essentially a sparse matrix. Like most of the elements are 0. Like, so you do have obviously it kind of has a block diagonal structure where the diagonals are 0, and then within every block you kind of have a pattern of zeros and non-zero blocks. But yeah, so I expect it to be a sparse matrix generally as well. Yeah.
Any questions online? That seems to be the case. Let's thank the speaker again.
Thank you.